Hey folks, welcome back. We are into particle systems. So we have this example here, and the craft goes through position, breaks apart, and we're asked to find the position of one of the pieces. So in order to do that, we need to build our equation set. So this is a part where you're going to be taking notes. We start with Newton's second law, F equals ma. And the good news, I guess good news and bad news about chapter 14 is that really the only difference is that, right? So instead of one force now, maybe we have many. Instead of one mass and acceleration, now maybe we have many. Similarly, if we think back to moments, some of the moments, let's see, moments about some point 0 equals r cross f. So now, many moments and potentially many r cross f's. So we'll use this instead, and this becomes the sum of all of the i's crossed with the masses and accelerations, which we don't actually use here, but we build it. We use this as our stepping stone into the equations that we'll actually use. Note, we could, if we have things that are accelerating in many directions, but the computation becomes really unapproachable very quickly. So rather than focusing on the accelerations, we will integrate and focus on the velocity, so momentum. And these we will be using. So the integral of this is about v I, right? So the derivative of velocity is acceleration and vice versa. We call this L, right? L linear momentum. And the L here is the summation of all of them, which is conserved, right? And similarly, we have angular, we call it H, H sub 0, and that is equal to the sum of all of the i's crossed with mi vi, right? So the sum of the moments, and again, the h dot is equal to m, right? So there is this one-to-one relationship. And you can imagine here mv, right? So the total mass and the velocity of the midpoint is going to give us the same thing. Mi vi, right? And we would use this if at one point they're all together and at the next they're broken apart, right? So something like this. And with this kind of thinking, we can actually go into position. And in position, we say m r is equal to the sum of mi r I, right? We need this one. So we're going to keep this equation. We will keep these two. And this one. So these we'll put into our list of equations. And the r's here, we should talk about what these r's are. So in general, sometimes we see this as r bar, and r bar is the relation, the total r from the center of gravity g, right? So if we have a system like this, and let's connect them for now. Then between them, we say there's going to be some point G. This will be our, in this case, sphere A. It's got MA, right? And similarly, sphere B has MB, right? So what we can do is we can define lengths. Call this RB, right? And it's the distance there. Call this RA, this distance. And R is the overall distance between them. Right, so clearly RA plus RB equals R. We know that. And also from the moment analysis, we can find that MA-RA equals MA, or excuse me, not MA, MB, RB. And we will want to remember these because often we're given that there is some point G about which we need to consider the moment calculations, right? So these R's are these R's, right? So in order to use this at all, we need to know where the center of gravity is. And this is really just the panel method that we were using back in statics. So these are the equations that we need here, and we're going to need those for lots of stuff. I think here, though, we're not going to need them all. Let's write them down anyway. Okay, our equations, what do we have? We have L equals MIVI. And I'm just going to extend this and say MV bar, then MR bar equals the sum of those, and this is linear, or excuse me, angular momentum. The angular momentum is the sum of R cross MI, excuse me, MIVI, and RA plus RB equals R, and MA VA equals, that's not V, that is an R. Okay. All right, so at those, let's look at this example problem, see if we can put some of this to work. So we have, we're given that there is a spacecraft and it is passing through this point at the origin. And as it passes through the origin, it has a mass of 200 kilograms, a velocity of 150 meters per second in the I direction. It explodes. And 2.5 seconds after the explosion, it is in 3 pieces, and A, B, and C, each of which has a mass. And we know the position of 2 of the pieces. We're asked to find the position of the 3rd piece at t equals 2.5 seconds. Something important to know is that if we have a single item, here we have MV, right? And then we have explosion, and then we have 3 pieces, or however many, then this is internal. It was not acted upon by anything outside. So the equation holds, right? So this equation, this conservation of linear momentum, it still holds. And that's true for any system. If there's no change in the energy from the outside, then the momentum is conserved. So at any rate, we need to find the position of C. So our overall strategy is going to be the conservation of linear momentum. So we have velocity and we have position. And the way that we relate those to each other is that we say that our bar is, so at the beginning, we have position 0, but what we're interested in is the position of this if it had continued, right? So that is V naught T. So 150 times 2.5 seconds. This is in the I direction, right? And that's going to give us 375 meters in the I direction, right? No, here, J, okay. So now we can use the same equation and we say MR bar is equal to the sum of MI RI, right? And so if we write this out, then M is 200 times 375 I is equal to, now we just plug things in, and this will be the mass times R for A and for B. So that is 100 times 555 is 5,500 I minus 180 100 J plus 240 100 K. For B, that's plus, what is that, 153, is it right? Yeah, 153 100 I minus 7,200 K, and then we bring in our C component. So it's going to be 40, and let's make RC. Let's make that RX plus RY plus RZ, just to make it easy for us. So that's going to be plus 40 RX, I direction, plus 40 RY in the J direction, plus 40 RZ in the K direction, right? That's writing as promised. So what we can do here is divide this out by direction and solve each direction for Rx, Ry, Rz, and then we're there. So in the X direction, in the I direction, what we have this, which is 75,000 equals 5,500 plus 24,000. Wait, that's K. No, we're not. We don't want that one. We want 153. And then Rx. Okay, and when we solve this, then we get that Rx is equal to 105 meters. Okay, similarly, in the J hat direction, we have no R in that direction, so 0 equals minus 18,000. There is no J component in B, so it's going to be plus 40 times RY. right, which gives us our y is equal to 450 meters, right? So you just add 18,000 both sides, divide it by 40, and that's what it gives you. Then in the k direction, what do we have? We have 0 equals 24,000 minus 7,200 plus 40, and that's plus 40 times r sub z. And when we solve that, we get rz is equal to minus 420 meters. So the net is RC, which is what we're after. It is equal to 105, 450 minus 420, and that is in meters. So in general, we're going to use conservation strategies. So conservation of momentum, both linear and angular, and then those conservations will be in terms of generally in position and velocity. And in the next example, we'll start thinking about angular momentum. So hope you enjoyed the video, and thanks for watching.